All right, so previously we had volumes by disks and washers. And sometimes the volume formula you got, the integral was too hard to do. Unlike derivatives, where you can do derivatives step by step, and for all your standard functions and operations, if it's product, you go to the product rule. If it's a functional function, you go to the chain rule. You can take the derivative. Not so with the integrals, right? With the integrals, if you have an integral of product, there is no product rule. Integral of quotient, there's no quotient rule. Integral of functional function, there's no chain rule. There are things close to it, but you can't just go step by step. Some integrals you just can't do. So when you come up with a hard integral, you can find a volume by disk or washer. Sometimes this makes it a little easier. And we recall that we had this kind of situation for cylinders. If you had a plane region, like this, x going from A to B, bounded below by the x-axis and above by a curve y equals f of x. Suppose we spun that around the y-axis, generating a solid that looks like this. So it's got this dish out in the center here and then a hole in the middle. And here's the counterpart to this side in the flip. And so you've got a solid generating by revolving this plane region around the y-axis. What is its volume? Well, we said that with a little bit of work, this was the integral from A to B of 2 pi x f of x dx. That's the volume formula for cylinders that we derived right at the end of the last time. We were running out of time. This is hard to remember. There gets to be a lot of formulas, right? And the thing to do is think of easy ways to remember them, just like when we had the method of disks. How do we say what the volume by disks was? Remember, that was a little different. If you revolved it around the y-axis, some plane region, here what you did was you took an integral with respect to y. You look at this. Here's a washer, for instance. You can say the volume is integral from, and you went y going from C to D. All right, this is hard to see, I know. But it's pi times radius squared, where the radius you had to figure out f of y, f2 of y squared minus f1 of y, where f2 of y was the outside radius, and f1 of y was the inside radius. And so you can think of pi r squared minus pi r squared dy. The volume integrating with respect to, for cylinders, integrates with respect to x when you revolve around the y-axis. So it gives you that advantage of going in the other variable. And the idea was here you had to think of the typical disk. I don't want to spend too much time on this, but if you had, say, the same solid here, what you had to do was think of the typical disk. And the disk had an inside radius, f1 of y, and an outside radius out to here. For the outside of this, you got cross sections or disks, and you're thinking of filling up this volume with disks of this solid got by revolving the plane region. And so you'd integrate the area of the typical disk. F1 of y is the inside radius, F2 of y is the outside radius. And so you'd integrate the area of the typical disk at y, F2 of y squared times pi is the area of the outside disk minus F1 of y, squared dy. So pi r squared minus pi r squared is the area of the outside disk minus the area of the inside disk. You thought of integrating the area of the disk, y going from C up to D. Right? So you integrate the disk area. Similarly, this one has a similar way of thinking of it, right? Pi r squared minus pi r squared is the area of the typical disk. This one, you're thinking of the typical cylinder effect. Remember how we filled this up with thickened cylinders? Maybe it's been a while, had been a week. That's why we need to have a little review here. but you consider the typical cylinder at X, and you're taking vertical cylinders here, X going from A to B, if you recall. And you have to figure the area of the typical cylinder. That's what this is. This is 2 pi radius times height. 2 pi radius height. And that's a way to remember this. It's the area of the typical cylinder. You're integrating the area of the cylinder, X going from A to B. So that's how you do this. Just like to figure the volume by disk, you found the area of the typical disk integrated from C to D here. Now we'll take the area of the typical cylinder and integrate it from C to D, because after all, X is the radius, right? This is the radius of the cylinder, X, and this is the height, F of X, right? So it's 2 pi radius height. And I think that's an easier way to remember. If you just try and cram down the letters, it's so easy to forget. But remember, the volume of a cylinder, or the area of a cylinder, is 2 pi radius height. All right. Because the circumference is 2 pi radius, and then you multiply by the height you lifted it to get the cylinder. Then you can remember this formula for the for finding volume by cylinders. All right. So I just wanted to say that this is the formula. This is our star formula. It's really only one in the whole section, except that there's also an equivalent formula. If the cylinders go the other way, then you have to do a formula for Y also. We'll mention that in a while. But it's just one formula and its counterpart in the Y direction. So here's a good problem. Suppose I take the region below y equals x squared. I'm sorry, x cubed. Above y equals 0. And bounded by x equals 1. Is to be revolved around the y-axis. To create a volume. Find the volume of a solid. Try to stand in front of that. So that's the idea. Think of this picture. I can stay with the camera here still. These problems often require drawing these pictures. So you take y equals x cubed. Remember what y equals x cubed looks like. It's this kind of a shape. It's a little steeper than a parabola, like that, and then it goes down on the left and up on the right. Here's y equals x cubed. And then we've got x equals 1 looks like this, right? And we've got the curve y equals 0 that looks like this. And we're talking about the region between those three things like this. So part of the problem is just be able to draw these plane regions. And suppose that's revolving around the y-axis. You just kind of draw a revolve point going around the y-axis. And this plane region, it's got its mirror image over on this side. And this is kind of like a telescope mirror, right? You maybe got a y equals x cubed mirror. It wouldn't be a telescope mirror, but some sort of a surface here. And you've got this hole cut out in this solid here. How do you find the volume of this? We don't need this part of the curve. Volume we got by revolving this plane region around the y-axis. Well, we simply follow the formula. We say it's the integral from a to b of 2 pi radius height with respect to x if the cylinders are perpendicular to the x-axis. And what you do is you just draw the typical cylinder at x like this. And the idea is you're filling up this volume by a sequence of cylinders. And so at x, the height of the cylinder, f of x, is equal to x cubed. That's the height. And x is the radius. So this, and apparently the cylinders start down here at y equals 0. Where do they stop? Well, you have to find this intersection point, right? This is where they stop right here. You go from C to D. Sorry. It's on the x-axis from here to here. You have to find this point and find where this is. And if you intersect y equals x cubed with x equals 1, you get x equals 1. And so the cross section, the cylinders go from x equals 0 to x equals 1. Right? Minimum cylinder starts out here, and then you get bigger and bigger. Here's the typical cylinder at x. And the largest cylinder is this one right here when x equals 1. So this is the minimum radius. To the maximum radius on all these cylinders. And I've got 2 pi x, and then the height is x cubed. Oh, this is easy, right? I just take the 2 pi out, and I have to integrate by the power rule, x to the 4th of its x.
Professor, could you move the camera just to the right?
Yeah.
Your left, just a bit.
I need to do that, and I forgot.
Thank you.
All right, so this is going to be 2 pi x to the 5th over 5, evaluated at 0, 1, or 2/5 pi. There's the volume of this one. That's the simple case. Like that. Now I want to step it up just a little bit more. You can see from this that you really don't have to do what's in the theorem there, 2 pi x f of x. If you're bounded instead on top by a top curve and on bottom by a bottom curve, you can generalize this formula. This generalizes when the bottom is not the x-axis. And you can use the similar formula, just remembering 2 pi radius height. So here's the next example. Suppose I revolve the region between y equals 2x and y equals x squared about the y-axis, and find its volume. The idea here is that you've got y equals x squared, the basic parabola, and the line y equals 2x. Slope 2 through the origin. So the parabola y equals x squared goes on like that, the line goes on like that. The region between them then is just like this. No longer is, when I revolve this, is the base of the solid the x-axis, right? I'm now taking this region here, I revolve around here, it's the mirror image over here, and I've got a cone cut out of this parabolic solid here. What is the volume of this thing when I revolve it around like that? So I can't use the formula, but it is completely analogous. I just say volume equals integral from A to B of 2 pi radius height. F of x, I'll write the same formula, but now f of x is the height of the typical cross section instead of the function on top. Height of the typical cylinder, excuse me. At x. So you draw the cylinder again. At x, when you're revolving around the y-axis, you've got this cylinder, and you're thinking of filling up the region with these cylinders. So now f of x, the height, is actually the top function minus the bottom one is 2x minus x squared this time. So when I'm going to find the volume here, I integrate, well, the cylinders start at x equals 0 here, and then what's this intersection point? This is where they end, right? So I can find out by setting these two equal, x squared equals 2x. Well, you can solve this one by factoring x squared minus 2x equals 0. That's equivalently x times x minus 2 equals 0. Oh, we've intersected x equals 0 and x equals 2. So you solve these kind of simple equations by factoring. And so this goes from 0 to 2. That's where the two intersection points are. So now the minimum radius, I'm thinking of a little tiny cylinder down here degenerating to 0 radius. And then the biggest cylinder is degenerating to this little circle up here, right? You're taking cylinders higher and higher to fill this thing up. And the last one is this little ring. And so the radius runs from x equals 0 to x equals 2, the radius of the cylinders. And at x, what you had was 2 pi radius x and height 2x minus x squared. So despite that they just give you that one formula, if you replace f of x instead of the height above the x-axis with the height of the typical cylinder, you get this formula. All right, so we can do that one. Let me carry it over here. So I can pull the 2 pi out and take the integral from 0 to 2 and multiply x times 2x is 2x squared. And the x times minus x squared is minus x cubed. And this then gives me the volume of this solid with a little cone cut out in the middle. Let's see, it's 2 pi integral of 2 times integral of x squared gives me x cubed over 3 by the power rule. Integral of x cubed gives me x to the 4th over 4 by the power rule. I'm going to plug in 0 to 2 this time and take the difference. I'll get 2 pi times. When I plug in 2, I get twice 8 thirds. Right? 2 cubed is 8. Minus 2 to the 4th is 16 over 4. And then I'll plug in 0. Well, 0 minus 0, I get that. Plug in the top endpoint, get this. Plug in the bottom endpoint, get 0. And we've got, let's see, 2 pi times 16 thirds minus 16 fourths. So you put these over a common denominator and call this 64 twelfths minus 48 twelfths gives you 16 twelfths. So it's 2 pi times 16 twelfths, doing some fast fractions. That's 4 thirds. So it's 8 pi over 3. Doing the fractions real fast. Which is roughly 8 since pi is around 3. It's a little bigger than 8. Okay. So there's a little more generality. Leave some of that up for you. Just like with the discs and washers, we can also revolve this around the other axis. Revolve the same region. Same plane region, but this time around the x-axis. And find its volume. So it really helps on all these to draw the picture. I'll draw the line y equals 2x. Curve y equals x squared. And if I revolve it on the y-axis now, this region, same region as last problem between these two curves now goes this way. Oops. And you've got this kind of a solid. longer. Isn't it? All right. With this cone-like thing cut out. What is the volume of this region? I get by sliding that around the x-axis. Well, now what you want to do is think of your typical cylinders going this way, right? So just like you do the typical disc and the typical washer for the method of discs and washers, in this one you draw the typical cylinder and you take the typical cylinder at y. And you say the volume formula is the same, just with respect to y instead of respect to x. And so this is the second formula I alluded to. We have, by analogy, just interchanging x and y to the first formula. The first formula was volume equals integral a to b of 2 pi x f of x. Was again 2 pi radius height for revolution about the x-axis. This is about the y-axis. About the y-axis. Revolution about the x-axis. Volume is an integral from c to d along the y-axis. 2 pi and the radius y. F of y dy. And again, you're thinking 2 pi radius height is what you're really integrating for this one also. So you draw the typical cylinder at y, and then you say, what is the radius given as a function of y? Well, that requires you to rewrite the equations. X is a function of y equals 2x is equivalently x equals 1/2 y. And y equals x squared is equivalently x equals square root of y. Right? So now what I do is I say the radius here is the rightmost curve minus the left one. That's this width here. The rightmost is the square root function. So I could call this f of y. Is the square root function on the right minus the 1/2 y function on the left. And so now this is the height of the cylinder, right? And the radius is y. Right? So I'm going to put a road in here. So this integral can be accomplished. And then I have to go, because I'm thinking of the cylinders, this is, again, the minimum radius cylinder to the maximum radius, but now in y. You have to think, here's a little tiny cylinder. The cylinders start off with radius 0 down here, degenerates to a point. And your maximum radius is way out here, right? This will be the biggest cylinder. Actually, it degenerates to this ring here, but the biggest cylinder goes out to this point where these two intersect. So you have to find the intersection point. Now we can set these two functions equal, or we can take the point from the last one using the y coordinate. But if you set 1/2 y, this function, equal to this one, square root y, what is y going to come out to be? Well, we can square both sides and say this is 1/4 y squared equals y. We can multiply by 4 and get y squared equals 4y. We can subtract and factor y squared minus 4y equals 0. Evidently, y times y minus 4 equals 0. But you just by hook or by crook using algebra, set these two things equal and solve, and we got y equals 0 and 4 now. So x went from 0 to 2 along this axis. Y goes from 0 up to 4. The maximum cylinder radius is 4. You can think of filling the thing up with. Here's another cylinder at this point, right? So you got cylinders, narrower but further out cylinders until the last cylinder degenerates to this ring out here at radius 4. All right, so this one now is going to give me the integral from minimum y radius 0 to maximum y radius 4, 2 pi y. F of y is that difference in the two functions there, square root y minus 1/2 y dy. So it's just getting a little trickier all the time, right? See if I can move this over a bit. Okay, and I just need to be able to evaluate that integral now. Let's see, it's pull the 2 pi out because it's a constant. Integral from 0 to 4. And then y times square root of y. You want to get the square roots out of there, right? You want to use fractional exponent because that's what our rules are in terms of. So y times square root of y is actually y to the 3/2. Our formula is for fractional exponents, not for radical signs. And then y minus times minus 1/2 y is minus 1/2 y squared. Now we see how to do it, right? The integral of the difference is the difference of the integrals. When we integrate y to the 3/2, we get y to the 5/2 over 5/2 by the power rule, right? Y to the n and y to the n plus 1 over n plus 1. Then there's minus 1/2 multiplying the integral of y squared gives me y cubed. I need to plug in 0 and 4 and take the difference. Well, let's see. Maybe I should do one more step and call this 2/5 y to the 5/2. And this one could be called 1/6 y cubed. I'll plug in 0 and 4. That'll make it a little easier. Well, 4 square root is 2 to the 5th power is 32. So you take 4 to the 5/2, you get 32, right? 2/5 times 32, right? Square root of 4 is 2, and then 5th power of that is 32. And then minus a 6th, 4 cubed is 64. Right? Oops, yeah. So now, let's see, I got 64/5 minus 64/6. 64 times 6 over 30 minus 64 times 5 over 30 makes 64 over 30 or 32/15. 2 pi times, now let's just write it out. Pi times 64/15. For a second. This is 32/15. Yeah, 64/30 is 32/15. 64/15. Oh, that's pi. There we go. Well, I did those fractions fast in my head, but if you bought one of those expensive calculators I suggested for this class, the TI-89 or the Inspire with the CAS, when you put these fractions in, it will automatically reduce them. It's one of the really nice things about those calculators. You can also do them online, of course, if you're doing your homework on certain software packages. All right, so 64 pi over 15 gives us the volume revolving the other. There's an integral with respect to y. Okay, any questions on that? Does that make sense? There's one last thing that's done in there just to generalize this a little bit more. I'll mention it in passing. Okay. You can also revolve around other things than the x or y axis, although I think really ideally you don't want to do that. But they give you a couple of them here just to remind you that that's possible. Here's a, let's see. Let me just do this. You can also revolve around other lines. than the axes. Just by thinking of the formula. For instance, if you revolve around the a line parallel to the y-axis, you can take integral from x going from a to b of 2 pi r of x, h of x dx, where you just think of this as the radius at whatever point you're at, and this is the height at whatever point you're at. For instance, if I take the curve y equals 2x minus 2, and the curve x equals 2, and the curve y equals 0. These bound the plane region. Suppose I revolve this instead of around the y-axis about the line x equals 1 and find the volume. You just use this formula instead of 2 pi x f of x, it's just 2 pi radius height. Because that's really what we're after in the first place, that formula. Again, draw the picture. And we'll say, let's see, x equals 2 is a vertical line. Y equals 2x minus 2. How do I sketch that? All right, it's y equals mx plus b. So I can plot slope 2 and y-intercept minus 2. I'll go down here. All right, x equals 2. And this has y-intercept minus 2 and slope 2. So it's going to come up like this with over 1 up 2, over 1 up 2, which puts it up here at y equals 2. And then I've got x equals 2, y equals 0. That's this one. Here's the line y equals 2x minus 2. If you make a careful drawing, you find it's actually this triangle. Right? So there's the plane region you're going to revolve, but now you're going to revolve it instead of around the y-axis like before, we're going to revolve it around this line like x equals 1. And so now you observe what you get out of this. Is this solid, right? It's got a cone cut out in the middle like the other example, but you revolve this plane region and get this volume. And I wonder what the volume of that is. I think it's better to set up the problem where you revolve around the y-axis, but if you do it this way, you can still say it's the integral from a to b of 2 pi radius height dx, and you integrate with respect to x if the cylinders are stacked along the x-axis like that. You integrate with respect to y if they're the other way, and this is different from the disc and washers form. If you use washers, you take the washers this way and do an integral with respect to y, right? 2 pi outer radius squared is a function of y minus inner radius squared is a function of y. So this gives you an integral with respect to x if disc and washers use y, and an integral with respect to y if disc and washers use x, which is one of the reasons it often gives you a formula that maybe you can integrate with the other one does. But you just have to say from the minimum x to the maximum x, we'll integrate from x equals 1 to x equals 2. Minimum value of x to the maximum value of x, going from the inner radius to the outer radius. And then 2 pi, and what is the radius? The radius is the, if I draw the typical cylinder in here, at x. And I say, what's its radius? Oh, it's x minus 1. And if I'm at x, the radius of the cylinder is x minus 1. Distance here from x back to 1. And then what's the height? If I'm at this point, it's the top function minus the bottom function. So the height is then y equals 2x minus 2, the line, less the x-axis, 0. So the height is just 2x minus 2 dx, and you can evaluate this interval to find the solid. So the 2 pi radius height formula is a little more general, all around the other axes. This is integral from 1 to 2, pull the 2 pi out. And then you have to multiply this thing out. 2x squared minus 2x minus 2 more x is minus 4x plus 2 with respect to x. This makes 2 pi times 2x cubed over 3, integrating this one, minus 2x squared, integrating this one, right? 4 times x squared over 2 is 2x squared, plus 2x. Put in 1 and 2 and take the difference on this one. So when I put in 2, I've got 16/3 minus 8 plus 4. And when I put in 1, I'll get 2/3 minus 2 plus 2. Putting in x equals 1, and these will cancel. Let's see. Minus 4 plus 16/3 gives 4/3 minus 2/3. It looks like it comes out to be 2/3 if I count. That's fast fractions, but anyways, just adding fractions. Times 2 pi. I guess it'd be 4 pi over 3. But the point is simply the formula generalizes. Well, I hope I didn't spend too much time at that. I think I'm going to go off the end here. Let me just over a little. Sorry about that. I think that covers all the cases for the method of cylinders. It's not a major method of the semester. It's just an alternative to discs and washers that do pretty much the same volumes. All right, so we're doing lots of applications. We got areas by cross sections, areas by discs, areas by washers, areas by cylinders. What else can we do? The next one is arc length. All right. So arc length has this prescription. If I have a curve, y equals f of x, how am I going to say how long that curve is between different points? Say between x equals a and x equals b. Here's one way to do it. We can think of estimating it by breaking this thing up into a bunch of sub pieces. Like that, we could increment the x-axis. This is one of the reasons you did so much gory detail on finding areas below curves. Is that idea of partitioning the x-axis applies to these other situations. If I call this x0 and this x1 and this x2, all the x coordinate where I take these spots, they don't have to be equally spaced. In this case, let's say I go up to xn. In general, n, I partition the x-axis into n subintervals. All right. It's not. There we go. So I'll partition the x-axis from x0 to xn, n intervals. And I'll call the widths of these just like we did in calculus 1, delta x1 means x1 minus x0. All right. Delta x2, the width of the second one, means x2 minus x1. And finally, the last one here will be delta xn is xn minus 1. So partition the x-axis up just like you did in calculus 1, and then say an estimate for the arc length of the curve is take a line segment from here to here plus here to here, because we know how long a line segment is. We got the distance formula, right? And we'll call this L1, L2 up to Ln. We can estimate the arc length L, maybe that's what we want to call the arc length of the whole thing. The L is approximated by the sum k equals 1 to n of Lk. In other words, sum up L1 plus L2 plus L3 plus Ln. That's an approximate arc length. But what are these arc lengths? Well, if we take the kth line segment here, what is its length? It goes from this point here with coordinates xk minus 1, f of xk minus 1. And it goes to the point here with coordinates xk, f of xk. All right, so that's the kth line segment. And what's its length? That's what Lk is. Lk, by the distance formula between these 2 points, is in the square root of xk minus xk minus 1 squared plus the difference in the y coordinate squared, right? Yk, let me put it over here. Let's put it over here. Lk is the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared. That's the distance formula, right? So xk minus 1 squared plus f of xk minus f of xk minus 1 squared. X coordinate squared plus y coordinate difference squared, square root. That's what I'll put in here. Square root of xk squared plus f of xk squared. All right, so that's an approximate arc length now. Well, we can do a little trick here. Remember, xk minus 1 is what we call delta x1, delta xk. So this is the sum k equals 1 to n square root of delta xk squared. And this one here, xk, can also be written as xk minus 1 plus delta xk. And then this one is minus f of xk minus 1. So xk we'll just write as xk minus 1 plus delta xk. Sorry, it's getting a little tedious. Let me know if it gets hard to follow. But this is a way of summing up right? This is the length of the kth arc segment, line segment, by the distance formula. That's all it is. And now you divide inside by delta xk squared and multiply outside by delta xk, and you rewrite this as the sum k equals 1 to n. Divide inside by delta xk squared, and I get 1 here. And here I get f of xk minus 1 plus delta xk minus f of xk minus 1 all over delta xk squared. So that's dividing the inside by delta xk squared, and then I can cancel by multiplying outside by delta xk, right? If you move that inside, it would be squared, it would cancel this one. So there's another way of writing the arc length. But now what does that look like? here comes the calculus trick from calculus one. Remember all those theorems you memorized, the intermediate value theorem and the mean value theorem, all those kind of things? What is this from calculus one? Yeah, if I took the limit, it would be the derivative, right? This is f of x plus delta x minus f of x all over delta x. That's the slope of the secant line. In particular, if you take its limit, it becomes the slope of the tangent. There was a theorem that you had in calculus one called the mean value theorem for derivatives. And I'll just remind you of it a little bit. By the mean value theorem for derivatives, also one for integrals. If you take y equals f of x on an interval a, b, here's what it says. And you take the slope of the secant line here is f of b minus f of a over b minus a, right? The rise over the run is what this is. And that's the slope here of the secant line, one that goes through the function of 2 points. The mean values theorem says that there's somewhere, for derivative, says that somewhere in between a and b, there's at least one point where the slope of the tangent line is equal to the slope of the secant line, provided that the derivative is continuous. So we'll say if this, we have that f prime of c is equal to f of b minus f of a over b minus a for some c in the interval from a to b. And maybe more than one value of c. That's the mean value for the term for derivatives, provided f prime is continuous. This is guaranteed. Has to be continuous on the. Well, guess what? If we assume that f is continuous over here, this is a secant line. If you think of this as b and a, and this is b minus a, because it's the increment. What we have now is that L can be rewritten as some k equals 1 to n square root of 1 plus, and this being the secant line, we can rewrite it as f prime as the slope of the tangent line for some c in the interval. And then delta xk on the outside still. So this one becomes this one, just replacing this with the derivative somewhere in the middle by the mean value theorem. And this is true for some c in the kth interval. On the screen, yeah. For some c in the interval from xk minus 1 to xk. Now we've got it, because now what we can do is this. Camera again. This is a long derivation, but I think it's really worth the insight into what you're doing. If I should say this is not equal to, it's approximately equal. Right, because this is just the sum of the lengths of the line segments. And maybe I should call it CK here because there's one for each interval. So in each interval, there's a point CK where that's true. Now, in the limit, as the number of intervals n goes to infinity, with the widest one going to 0, is important. With the widest interval going to 0 width. This becomes exactly L is the limit as n goes to infinity, or the book will write width of the partition goes to 0, of sum k equals 1 to n, square root 1 plus f prime of ck squared delta xk. And what is that? This is by definition the definite integral. Remember, we find the definite integral of functions. It's a little more. By definition of the definite integral, this is actually the integral over whatever interval you're talking about. Here it's from a to b. Of this function, put in x instead of ck. So it's square root 1 plus f prime of x squared, and the delta x becomes a dx. And this notation means this. Remember, this is the definite integral definition. When you write integral from a to b of f of x dx, what does that mean? It means, let's call it g of x. It means limit n goes to infinity with the widest interval going to 0 of sum k equals 1 to n g of x, let's say ck delta xk, where ck can be any point in the interval whatsoever. This is the definition of the definite interval. That's precisely what we had here with this our g of ck. Right? Or they'll sometimes call this xk star instead of ck, but it's the same thing. And so when this is the function g of ck, we write as the integral of g of x, and this notation means this. So just by definition of the definite integral, this is precisely this integral. That's it. That's the derivation of the formula. We have derived that for a function with a continuous derivative, it's called a smooth function sometimes. If it has a continuous derivative, it's smooth. The arc length is actually equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. There it is. That took up the whole board. That was not a short derivation, but that's it. And now the good news about this after all this work is that there's only one formula for the whole section, except that you can turn it the other way. Also, if x equals f of y is has continuous derivative, you can turn it the other way and say that the arc length is the integral continuous on an interval of y values from c to d. You can say that the arc length is the integral from c to d of the square root 1 plus f prime of y squared dy, and this takes the arc length the other way. You're going from c to d, taking a function like this, x equals f of y, and finding its arc length. And it's the same thing, line segments across here. So you can do it with x or with y. It's really just one formula, turned two different ways. If I call this 1 and this 2, all you have to do is change a and b to c and d and change x to y, and that's the whole formula. Okay, so now the object is to do a few problems with those, right? Suppose I wanted to find the arc length of the curve y equals x to the 3/2 from x equals 0 to x equals 1, right? One bad thing about this formula, maybe you've noticed, is it gives you a nasty integral. It's usually difficult to evaluate. You have to pick a function real nice to be able to actually evaluate the integral. But the good news is that with modern machinery, you guys are familiar with modern machinery, you can do numerical methods that approximate this about as accurately as you want. So you can get a good decimal approximation. You just don't get a formula like we will here. So if here by equation 1, since y is given as a function of x, and x going between two numbers, we use formula 1. If y goes between two numbers, and x is given as a function of y, we use formula 2. Right? We'll say the length is just the integral from a to b, square root 1 plus, I'm just copying the formula, f prime of x squared dx becomes, x goes from 0 to 1. Should draw the picture again just to if y equals x to the 3 halves, a little less steep than a parabola, but it's bowed up like this, going from x equals 0 to 1. It looks about like that, right? X to the 3 halves. And we want to know how long is that arc. Right? So we integrate from 0 to 1, the x values along the x-axis, and then square root of 1 plus the derivative of this curve squared. Well, what's the derivative of x to the 3 halves? Right? We call it f of x. F prime of x is 3 halves x to the 1 half, right? So let's say this is 3 halves x to the 1 half squared. And now you see where this is a cooked problem. But we can actually do the integral. In general, this thing is just difficult to find a formula for. Integral from 0 to 1, square root of 1 plus 9/4 x dx. Remember how to solve this one? How do we integrate this? One of the things that's going to come out in this section, it is going to make you review some of your integration formulas because it's hard to give an easy integral. You get some hard ones in here. How do I integrate that? Here's a good idea. Remember, u substitution. When you see a function of a function, a good hint is to let u be the inside function. Sometimes that works, sometimes it doesn't. But you think of it and you see if it works. I'll let u equal 1 plus 9/4 x. Then it'll be square root of u instead of square root of this, right? So maybe I'll get an easier integral. But if I'm going to do that, I have to also substitute out dx in favor of du, where du is the derivative of u dx, right? So what is that? Derivative of u is just 9/4, right? 0 plus 9/4 times 1. So this is 9/4 dx. And if du is equal to 9/4 dx, I multiply by 4/9 and say 4/9 du can replace dx. So that's the substitution. I'll substitute out dx, replace it with 4/9 du. And I'll substitute out 1 plus 9/4 x and put in u. Now this becomes the integral of square root u, much easier. 4/9 du. There it is. I can do that one. So there's a good substitution. Over here. Let's see. That's 4/9 that comes out. Square root u I can write as u to the 1/2. Remember, always write it with a fractional exponent, so you know the rule that applies. This is the power rule, right? And the integral, I can't, why don't I write 0 and 1 here? What's wrong with that? These, if I just write 0 and 1, these are the values I'm going to evaluate u at, but x went from 0 to 1, not u. So if I want to change the endpoints on here, I can solve this and put it in terms of x and then put in x equals 0 and 1. But one thing you want to learn how to do in this class, because a lot of books do it, is to change the endpoints for u. You say, if x goes from 0 to 1, what does u go from? Right? So you can put over here somewhere. Well, I just need a little more room here. You make this substitution. You just say, well, when x equals the bottom endpoint here is 0, what is u? U is equal to 1 plus 9/4 times 0 is is equal to 1. Similarly, when x equals the top end point here, 1, 2 is equal to what? 1 plus 9/4 of 1 times 1 is 13/4. So this integral will go from 1 to 13/4, and then I'll never have to put x back in. Alright? So let's do that. This integral goes from u equals 1 to u equals 13/4. And I've got 4/9. Integral of u to the 1/2, right? U to the n has the integral u to the n plus 1, or u to the 3/2 over n plus 1 is 3/2. Plug in 13/4 and 1 and take the difference, right? Well, let's see, 4/9 times the reciprocal of 3/2 is 2/3, so this is 8/27, right? Multiply 4/9 times 2/3, the reciprocal of this one. U to the 3/2, plug in 13/4 and 1 and take the difference. More room to there. So this is going to be 8/27 times 13/4 to the 3/2. Less 1 to the 3/2 is just 1. Right? So it's 8/27 times, well, 4 to the 3/2, take square root of 4 and get 2, and then cube it, you get 8. And 13 to the 3/2 is 13 square root of 13. So you get this result. You might go ahead and multiply this 8 in here now and say, well, this is 1/27 times 13 square root 13 minus 8. I would write it that way, or you just put this whole thing over 27. There we go, the arc length of that curve exactly. But you notice we had to pick a nice function to be able to do it. How about that? Just to exhibit the other formula, let's say, suppose we wanted to calculate with formula 2. Sometimes it's a little easier to do it in one variable than the other. So alternatively, we can calculate the same arc length by rewriting it. Y equals x to the 3/2 by taking the 2/3 power and getting x equals y to the 2/3, right? And here x went from 0 to 1. So when x equals 0, y equals 0 to the 3/2 is also 0. And when x equals 1, y equals 1 to the 3/2 is also 1. So once again, the integral will go from 0 to 1. And we get, by rewriting it in the other formula by 2, arc length is integral y going from c to d, square root of 1 plus f prime of y squared dy. Same formula, just going the other direction. Y goes from 0 to 1, just like x did, just for this particular problem. There's the endpoints that we just calculated. Square root of 1 plus, and now we need to write x as a function of y. Here it was. This is our x as a function of y. Y to the 2/3 prime squared. We need this. I need to write this somewhere here. So our function we're finding the arc length of is f of y equals y to the 2/3. Its derivative, f prime of y, is 2/3 y to the minus 1/3, right? Y to the n has derivative n, y to the n minus 1. So this one here that I'm going to square is f prime of y is 2/3 y to the minus 1/3. And I need to square that, dy. This arc length formula is supposed to give us the same number. All we're doing is integrating with respect to the other variable, thinking of the line segments where we incremented the y-axis instead of the x-axis, right? So let's see if we can do this integral. And again, setting it up is easy. It's the integral that's hard, right? This is the integral from 0 to 1 of the square root of 1 plus 2/3 squared is 4/9. Y to the minus 1/3 squared is y to the minus 2/3 dy. There it is. I need to be able to do that one. This one has a little harder trick that I want you to see because this once in a while comes up. Can you think how to do this one? The immediate thing to say is, oh, it's a function of a function. I can let u equal 1 plus 4/9 y to the minus 2/3. Why isn't that a good choice? You try this always when you see a function of a function, but often it doesn't work. It's because if I do this, I have to put du equals the derivative of that. 4/9 times minus 2/3 y to the minus 5/3. Oh boy, that's a mess now, right? dy. And I don't have a y to the minus 5/3 dy, so I'm just stuck, right? So that's not a good substitution to solve it. Instead, this is all the little leisure domain they call a little magic trick here, sleight of hand. You multiply on the outside by y to the minus 1/3, and on the inside by cancel it by y to the 2/3. All right, these will cancel each other. So there it is. These two cancel, and it's the same integral. But now look what I've got. This is integral from 0 to 1, y to the minus 1/3, square root of y to the 2/3 plus 4/9 dy. I do this because this is on the homework, and it's in most calculus books. Even another integration trick to keep in mind when you get out of the course. So now I can solve this one because now I fixed this just right. I multiplied inside and outside by just the right thing. So that now if I substitute u equals this, y to the 2/3 plus 4/9, du will be the derivative of that dy, right? Du is du dy, using the rule for differentials, is what's the derivative of y to the 2/3? It's 2/3 y to the minus 1/3. And then that multiplies dy. And now if I multiply both sides by 3/2, I'll get 3/2 du is y to the minus 1/3 dy, precisely what I have out here. So this can be substituted out. This is going to be u. But this part can be substituted out and replaced with 3/2 du. This thing in here can be substituted out with u, and you rewrite this as the new integral. 3/2 du replacing the y to the minus 1/3 dy, and square root u replacing square root of the mass. Now I've got something better. So it's just a matter of being clever on there. Multiply by the right thing inside and out to make the du out here that you didn't have before. This is a bad substitution because you didn't have the y to the minus 5/3 dy, you just have dy. But by making this multiplication, when you let u equal this, now you have du on the outside. So that's the idea. And now we'll change the endpoints again, or you can finish the integral and convert it back to y. But we'll make the observation that when y equals 0, what is u? U is equal to 0 plus 4/9 is 4/9. And then when y equals 1, the top endpoint, u is equal to 1 plus 4/9 is 13/9. So this will now go from 4/9 at the bottom to 13/9. Those are the values of u that I'm gonna evaluate this integral at, and I never have to convert back to y now. So let's see what we got here. Again, thinking of this as u to the 1/2. Let's rewrite this one time. This is 3/2, pull the 3/2 out. Integral from 4/9 to 13/9. U to the 1/2 du. That's what I get pulling the 3/2. And hopefully I didn't make a mistake in the first step, right? That's one of Murphy's laws, right? The mistake is always in the first step. We'll be here till tomorrow reworking it. But 3/2, integral of u to the 1/2, right? U to the n has integral of u to the n plus 1 over n plus 1. So it's u to the 3/2 over 3/2. And nicely, these 3/2 cancel. Right? And then I go from 4/9 to 13/9, put those two in and take the difference. So I have to take 13/9 to the 3/2 minus 4/9 to the 3/2. Well, this looks like 13 square root 13, right? 13 to the 3/2 is 13 square root 13. 9 to the 3/2, well, square root of 9 is 3, and then you cube that, you get 27. And then minus this one, 4/3 square root is 4/9 square root is 2/3, and then cube gives you 8 27s. And there it is. It looks like this is what you had before, right? It's 13 square root 13 minus 8 all over 27. Done with an integration with respect to y instead. But as you can see, this one is a little harder than the other one. Sometimes you just can't figure out how to do the integral one way, but maybe you can do it the other, so it's worth having the two forms. This is, after all, typically a hard integral because of that nasty square root. All right, any last second questions then? That pretty much completes all the things I want to do in that section. This is not a major section. It has one formula, and then it's the same formula converted with respect to y. Here's the homework that I'd like you to look at for next time. I'll have to send you probably an email to figure out what we're going to do. The university is changing the COVID policy we've got terrible numbers and, so I'll have to see what the policy is, whether we continue to have this, what do you call it? Part distance and part in-person class, or what we're going to do. But here's what I'd like you to look at. 5.3. This is on the method of cylinders. That's not a major topic. Just do 1, 5, 11, and 27. This will do some integrals where the cylinders are perpendicular to x-axis, in other words, where there's perpendicular to the y-axis, and that's all you need to do, just like we did today. 5.4 is on arc length, just like we did here. Look at 3, 9, and 13, and we've already done some of this. So there's 7 problems to try for next time. Cylinders and arc length. Lots of neat applications. It's amazing what you can do with calculus. You get all these neat formulas for, like, what do you want the volume of a cone, we said before, right? You can do it by doing the method of discs or washers, and now you can do it with the method of cylinders also. You get a formula for all these different solids that you've seen before. All right, well, that's a good stopping point then. See you on Monday then.
Professor,
Yeah.
how often do you check your email?
Every day, but I haven't checked it since like early yesterday morning, so I'm real late today just because of my schedule.
Okay.
But I'm gonna check it in. Started checking it earlier this afternoon. I didn't get through it all.
So if we email you questions for the homework, you'll just answer frequently more in the afternoons?
If you send me questions, I usually answer them sometime the next day. If I get them the same day, I might answer them the same day. If I get them the next day, I answer them the next day.
Gotcha. Thank you.
Yeah.
We got a question about the board too.
Yeah, can you move the camera so you can see the problems?
Which
The homework problems.
that one? Not this one, the previous one? The other side of the board?
No, that's what we need, the homework
I'm
problems.
sorry, this is the homework problems here, right. I'm sorry, I wrote them just off the board, didn't I? I'm so sorry. I gotta stop moving this camera so much. Yeah, here's the homework problem. I'm sorry I left off the end of this problem here too. Thank you.
Thanks.